Welcome to lecture 16 of Power System Protection course. So in the last lecture, that is lecture 15, we covered the Moore relay, which is one of the different types of the distance relays. So in case of Moore relay, we saw that also we derived the equation for operating characteristic, and from that we draw the operating characteristic in Rx planes, and then we found the impact of arc fault and Moore relay, then impact of normal load condition, then the power swing condition. So all these cases we discussed. Then finally we compared all the different variety of relays, distance relays, all the different types of distance relays. So now in this lecture also little bit we can see the comparison between distance relays. So now we can see there are already we have seen that we have three types of important relays in distance protection. That is, one is your simple impedance relay, reactance relay, then Moore relay, right? And we have seen that the operating quantity for simple impedance relay is current, and also it is same for the reactance relay. And for Moore relay, the operating quantity is the directional element where the voltage and current both are involved, and MTA can be adjusted according to the requirement. Similarly, in case of restraining quantity, for restraining quantity, the simple impedance relay, for simple impedance relay, voltage acts as the restraining quantity, and similarly for reactance relay, the directional element with MTA equal to 90 degree, it acts as the restraining quantity. And for Moore relay, the voltage in fact acts as the restraining quantity. Similarly, if we will see the directional property for simple impedance relay, there is no directional property at all, right? Because already we have seen it covers the 4 quadrant, right? And in case of reactance relay also, it has no directional property because it operates in both direction, in forward and the reverse direction, and it also occupies very huge area, right? And similarly in case of Moore relay, we have seen that it is directional relay, because as we adjust the MTA, the maximum torque angle, based on that the direction is adjusted of this Moore relay, and it in fact it occupies very less space. And let us see the performance and load. So if we will compare the performance and load with different types of relay, distance relays. In case of simple impedance relay, it restrains, okay, well restrains, and in case of reactance relay, it trips, because the operating point lies in the trip region, because it covers a very huge area in Rx plane. And in case of Moore relay, it in fact restrains, because it covers the small area and it is unidirectional. It lies in fact only in the first quadrant. If it is adjusted where it can be lie, right, based on the MTA, maximum torque angle. Similarly, we can see the effect of fault resistance on these different relays. So for fault resistance during the because in fact in practice almost all the faults are arc faults, so having some resistance. So simple impedance relay underreaches for this fault resistance, and reactance relay in fact reach well, because already we have seen, because of its parallel characteristic, it reaches well, that is the reach is unaffected. And in case of Moore relay, in fact it underreaches, and it is slightly more than the simple impedance relay. If we will compare the area occupied on Rx plane, then your simple impedance relay occupies moderate area, and your reactance relay in fact occupies very large area, and Moore relay in fact occupies the smallest area. And if we will compare the effect of power swing, in case of power swing the simple impedance relay maloperates, and in case of reactance relay it also maloperates because your power swing because it occupies very large area, and power swing, in fact whatever swing happens, whether it is small or large swing, it lies inside the trip region. And in case of Moore relay, in fact it maloperates, but its effect is very less as compared to the simple impedance relay and reactance relay. Already we have seen all these comparisons, and in this class let us see how we can implement a distance relay in a 3-phase transmission line. That is very important. So, distance protection of a 3-phase line, transmission line. So, in this we will cover, let us see how are we going to provide protection against all 11 shunt faults. Already we know that we have 11 shunt faults happens, that includes the phase faults and the ground faults, that is A to G, B to G, C to G, these are the ground faults, and A to B, B to C, C to A, ABG, BCG, CAG, ABC and ABCG, they are all phase faults already we have seen. And second question is in what way the CT currents, this is very important, and the PT voltage will have to be processed, because we will acquire the CT and PT voltage and it has to be fed to the relay unit, and how it will be processed, that is important, right. And third point is, can a single distance measurement unit look after all the phase faults as well as ground faults? Like in case of overcurrent relay, we put a single measurement unit, right, and that in fact that is okay for overcurrent relay. But in case of distance relay, is it okay the single distance measurement unit look after all the phase faults as well as the ground faults? If no, how many distance measurement units will be required for catering to all 11 shunt faults? So, this is very important. So, how many distance measurement units we need to put? So, what will be the setting of the distance measuring unit? This is more important, we will see it, and then we will see whether to measure the positive sequence impedance or negative sequence impedance or zero sequence impedance, which type of impedance we need to measure for comparison. Okay. So, let us see then one by one. So, let us consider a 3-phase transmission line, and where we can see this is your source and it is connected, it is feeding to a transmission network, and here we have the circuit breaker, and we have CT units and PT units. These are CTs and these are PTs, right. So, CT and PT. So, in fact from CT we will acquire the current and from PT we will acquire the voltage. Now, the question is how to combine these measured voltage and currents, and then we will feed it to the impedance relay or to the distance relay, and it will compare the impedance. So, for that region, how many units we require, how many distance measuring unit we require, and what should be the setting, how we will set this Z, whether in positive sequence impedance or negative sequence impedance or zero sequence impedance. So, let us see this one by one, and then after comparison it will give a trip command to the circuit breaker. Okay. So, presence of sequence components in various faults. Let us see the presence of sequence components in various faults, and then we will derive what combination will feed the voltage and current into the relay. So, already we know these are the different types of faults: line to ground fault, line to line fault, line to ground fault, and triple line fault. And for line to ground fault, obviously the positive sequence component exists, and also negative sequence component exists and zero sequence component exists, right. So, but for line to line fault, in case of line to line fault, only positive and negative sequence component is existing, but zero sequence component becomes 0. Similarly, for line to ground fault, all the components, positive, negative and zero sequence components are existing, and whereas in the 3-phase fault, that is we call balanced fault. In case of balanced fault, only positive sequence component is existing, other sequences are not existing, right. Okay. So, let us then say see one by one all these faults, and from these faults we will analyze using the sequence component network analysis. Using that, we will derive what component in fact we need. So, from this table we can say that for all the faults your positive sequence impedance is existing, right, whereas the negative and zero sequence components, they are sometime not existing, that is negative sequence and zero sequence network, they are sometime not existing for some faults, like in balanced fault, in line to line fault, the zero sequence component is not here, and in balanced 3-phase fault also the negative sequence component is not here, not there, right, negative sequence component network is not there. So, therefore, only we can say that the positive sequence component or positive sequence network is existing for all types of faults. That means, in case of all types of faults, we have the positive sequence network. Therefore, it is important to take the positive sequence impedance rather than taking the negative and zero sequence impedance, because they are not existing in some of the faults, right. So, therefore, we will focus on deriving the positive sequence impedance formulation, and out of that we will reach the final equation. Okay, so let us see one by one. Okay, now we will consider phase fault. So, in case of phase fault, let us consider the fault between this is a 3-phase transmission line, where let us say the phase fault is between phase B and phase C, right. Phase B to C metallic fault is considered. Now, we have the measuring parameters current and voltage. So, in each phase IA, IB, IC and VA, VB, VC, we have these measuring parameters. Now, if we will represent this fault in positive sequence network, okay, sorry, not in positive sequence network, in sequence network, represent this, let us represent this fault in sequence network. Okay, so let us represent this in sequence network, and if we will represent this, obviously we know for line to line fault we have positive sequence network and negative sequence network, they are existing and they are connected in parallel to each other, and the currents are flowing out of the network, right. So, already we have seen this representation when we talked about the fault analysis. In some of the classes we talked about fault analysis, and I have shown in that how to represent a network during the fault, during different types of faults. So, this also we have talked about, you can see it going back to those lectures. So, we have seen that in case of line to line fault, we have positive sequence and negative sequence network existing and they are connected in parallel, right. And this is the fault point. In fact, F1A and F2A, they are the fault points, they are connected together, right. Now, if we will represent it through the equivalent network, how it will look like, because the transmission line is existing between the fault location and the source or fault location. So, therefore, if we will represent the transmission line impedance in the sequence network form, that will show Z1 and Z2, they are the representation of the sequence impedances of the transmission line, and ZS1 and ZS2 are the source impedances sequence network, right. So U1 is your positive sequence EMF of the generator. Similarly, VA1 is the terminal voltage, positive sequence terminal voltage, and VA2 is your negative sequence terminal voltage. And IA1, IA2, they are the positive sequence and negative sequence currents respectively, and they are connected together, and this is your fault location. Okay. So where both the networks, positive and negative sequence networks, they are connected together. Okay. Now if we'll see what we are seeing here, if we'll write the network equation for this network, then what we'll write? We'll write this, in fact, VA1 for this net, because they are in parallel, so I can write VA1 minus IA1 Z1 plus IA2 Z1 minus VA2 equal to 0, because Z1 equal to Z2, in fact it is Z2, and because Z1 is equal to Z2, so I can write here Z1. So now just simplifying, I can write it as VA1 minus VA2 divided by IA1 minus IA2 equal to Z1. Okay. So our purpose is to find Z1 in terms of the sequence parameters, and we will convert these sequence parameters into the phase parameters. Okay. So how we will convert this phase into phase parameters? Just substituting VA1 and VA2, IA1, IA2 in terms of VA, VB, VC, IA, IB and IC. So if we will represent this, then how we will write this? So just by representing VA1 minus VA2, how I can, so VA1 I can substitute, VA1 is equal to 1 by 3 of VA plus AVB plus A square VC, simple. And VA2 is 1 by 3, already we have derived this during the fault analysis lecture. So you can see, go back and see VA A square VB plus AVC. So now substituting VA1 and VA2 in this equation, we will find that, and similarly we can substitute the currents as well. So currents I can write IA1 is equal to 1 by 3 IA plus AIB plus A square IC. Okay. Similarly IA2 is equal to, I can write 1 by 3 IA plus A square IB plus AIC. So now substituting the currents and voltages in this equation, we will obviously find VB minus VC by IB minus IC equal to Z1. Now our purpose is fulfilled, because Z1 is represented in terms of the phase voltages and currents, phase currents, which is in fact the measurable parameters. In fact, we are measuring the phase voltages and the phase currents, or line voltages, line currents. So VB minus VC, I can say this is line voltage, right. So therefore now I can say that Z1 is represented in terms of the phase parameters, which is the measurable quantity, or we measure through using the CT and PT. Okay. Now if we can measure VB, VC, IB, IC, I can find Z1, right. So this is your impedance, in fact seen by the relay, right. If I will feed these quantities, this is the impedance seen by the relay. Okay. So now I can set according to my requirement. So similarly, if we will see the ground fault, let us see the ground fault. For ground fault, let us consider the phase A to ground fault here in this phase A to ground fault, right, in this transmission line. And if we will draw the sequence network of this fault, then how it will look like? It is just a series connection of positive sequence network, negative sequence network and zero sequence network. Already we have discussed this in your previous classes during the fault analysis, that in case of single phase fault, your sequence networks will be connected in series, and it is connected in series. Now just representing it through the using the transmission line parameters, and the fault point is here, fault location, right, at this point. Okay, so now this is your relay location where we are measuring the voltage, in fact at the terminal of the generator, right, and that is shown in different sequence networks, in positive sequence network, in negative sequence network, in zero sequence network. Right, now writing the sequence network equation, we can write this, right. So this will be your sequence network equation. It is connected in series, so I can write VAO plus VA1 plus VA2 equal to IA1 Z1 IA2 Z1 plus IAO Z0, whereas this Z1 is in fact Z2 because Z1 is equal to Z2, so I have replaced Z2 is equal to Z1, right. Here we can see Z2 equal to Z1. Okay. So now from this equation we can say, so VAO plus VA1 plus VA2 is nothing but equal to VA. So I can write that is equal to IA1 Z1 plus IA2 Z1. So just by adjustment, so just by manipulating here, just adding IAO Z1 minus IAO Z1, and IAO Z0 was there, I have replaced here, and just here the manipulation happened. Okay, just manipulating, I found this, right. So I can write this equal to IA, because IA1 plus IA2 plus IAO, by taking common Z1 I will find IA1 plus IA2 plus IAO, that is equal to IA. Okay, so IA Z1 plus Z0 minus Z1 into IAO, right. Okay, so this will be your equation. Now little bit manipulation we will do. So it will be VA, I can write VA equal to, just by taking outside Z1, taking common Z1, I can write IA plus Z0 minus Z1 by Z1 into IAO. Okay, so I can say that however we know that IAO is equal to this, IA plus IB plus IC by 3. This is from the sequence equation, sequence parameter equation, right. And let us write this IA plus IB plus IC equal to I residual, right. So this is I residual, right. So I residual, in short form I have written I res, right. Then I can write this as VA equal to IA plus Z0 minus Z1 by 3 Z1 into I res into whole into Z1. Okay, and that will give me Z1 is equal to, if I will write Z1 here, Z1 equal to VA by IA plus Z0 minus Z1 divided by 3 Z1 into I residual. In this equation we can see that Z1 is in both the side of equation, in left hand side and right hand side. We need to eliminate Z1. So how we can eliminate? In practice we know that Z0, however in actual practice there is a definite relationship between Z0 and Z1. For 3-phase transmission lines, Z0 is actually 2.5 to 3 times of Z1. So let us consider 3 times in this equation now, and the exact relationship depends upon the geometry of the phase conductors and the placement of earth conductors. Let us assume here in this Z0 equal to 3 Z1. Now substituting this, what the equation will become? It will become Z1 is equal to VA by IA plus 2 by 3 I residual. Now Z1 is eliminated from the right hand side just by taking the empirical relation, and that I can write equal to VA by IA plus K I residual. K is a constant, right. So coefficient. So the factor K is known as the residual current compensation factor, or zero sequence current compensation factor. Okay. So, this is how we can say this is your zero sequence residual current compensation factor or zero sequence current compensation factor, right. So, now we can already we discussed how we can see the Z1 we found in case of single phase, that is ground, in case of ground fault. In case of phase A to ground fault, we found VA by IA plus 2 by 3 I residual, or I can say VA by IA plus K I residual. Similarly, for phase B fault, I can write VB by IB plus K I residual, right. Similarly, for phase C to ground fault, I can write Z1 equal to VC by IC plus K I residual. So, this involves this includes all the ground faults, right. Similarly, in case of phase fault, we found that in case of phase fault we found this Z1 is equal to VB minus BC divided by IB minus IC for fault between phase B and C. Similarly, for fault between phase A and B, I can write Z1 equal to VA minus VB divided by IA minus IB. This is for A to B fault, okay. And similarly, for A to C fault you can write, right. And this will also cover A to B to G, A to B to ground fault, and B to C to ground fault, C to A to ground fault, okay. So, in fact, this includes all, if you will see, this includes all the phase faults and all the ground faults, right. If we will see, if we will consider the 3 phase fault or balanced fault, that is very easily we can say how it can be done, because for balanced fault the sequence network, in fact the sequence network is only the positive sequence network is existing for the balanced fault, all others are not there. So, therefore, for 3 phase fault, if I will write the equation, I can write Z1 equal to VA by IA, right. And this, in fact, this equation will be applicable in case of 3 phase fault, because I residual in that case will become 0, okay. So, if I residual will become 0, then it will give VA by IA, simple, right. So, now we will see the complete protection scheme of a 3 phase line, how we can implement this. So, this is your 3 phase feeder where, sorry, 3 phase transmission line where our source is EA, EB, EC, these are 3 phase sources, and it is connected through the circuit breaker, this transmission line, and we have the measuring unit, we are measuring current. So, these are the currents, we are measuring IA, IB and IC. In fact, in order to find the difference of the currents, we have connected in the delta fashion, first one, and in second this is in delta fashion, and this is in star fashion, right. So, in star connection, where it is connected, in order to find the residual current IA plus IB plus IC in the secondary side of the current transformer. So, therefore, we need here 2 sets of current transformers, right. So, one set will give us the difference of the currents, that will give us IB minus IC, IM minus IB and IC minus IA, and another set of CT, another set of CTs will give me the residual current, that is IA plus IB plus IC. So, both the connection fashion of both CTs are, one is in delta fashion and other one is in star fashion, right. Now, I will see how the potential transformers are connected. So, we need the voltage difference and the voltages, single voltages and voltage difference as well. So, we can find the voltages directly from the PT, right. So, we can find the VA, VB and VC from each of the phase voltages, and if we will take the line voltages, that will give us the difference of the voltages. So, if I will take VA minus BV, that will give my VAB, right. So VAB will be VA minus BV. Similarly, your VBC will give me VB minus VC, VCA will give me VC minus VA, right. So so already we got these combinations of measurements, right. So we found the current difference, voltage difference, and the residual current, which is in fact required for our relay, right. Now we can see we need to combine all these settings. So therefore we can see here we need in fact we need the distance elements. How many distance units we need? 1, 2, 3, 4, 5, 6. 6 distance units we need, distance relay units we need. So to each of the relay units we will feed the different voltage and current. So we can see here to the first relay unit we are feeding VAB IA minus IB. The second relay unit we are feeding VBC IB minus IC. The third relay unit we are feeding VCA IC minus IA. Then to the fourth relay unit we are feeding VA IA plus KI residual. The fifth unit we are feeding VB IB plus KI residual. Similarly, sixth one we are feeding VC and current is IC plus KI residual. So we can see that different combinations is required in order to protect the 3-phase transmission line from all kinds of, this will give us protection from all 11 faults, 11 sound faults, right. So therefore this will cover all 11 sound faults, and in fact this will VA plus IA plus K residual will give protection from 3-phase balance fault, because in that case your I residual will become 0 and it will VA IA, that is VA by IA will give us Z, right. That is the impedance seen by the relay. So all these are in fact fed to an OR gate, because we don't know which kind of fault will happen in the transmission line, and the final output of the OR gate will be feeding to the circuit breaker trip coil, and it gives the command to the circuit breaker. In fact here somewhere it will be the circuit breaker trip coil, okay. So then from the circuit breaker trip coil it will go to the circuit breaker for operation. So any kind of fault, now this will activate, right, for any kind of fault, for single line to ground fault, double line to ground fault, double line fault, or triple line fault, or 3-phase balance fault, 3-phase to ground fault. For any kind of fault it will cover protection to the 3-phase transmission line. So this is in fact your complete protection scheme of a 3-phase line by using the distance relay, okay. So thank you very much. So we'll stop here, and in the next class remaining portion of the distance protection will cover, like carrier radar protection, what are the drawbacks of the distance protection, we will all cover in the next class. Thank you very much for your kind attention. Thanks a lot.